Right now, in this very moment, the Earth is pulling gently at every part of you, your hands, your breath, the weight of your head against the pillow, and this invisible embrace has not paused for a single second since you were born. Gravity, that quiet companion, is not truly a force at all, but something stranger, something the universe wove into the fabric of space and time itself. A curvature so subtle that we experience it only as the sensation of falling endlessly toward everything around us. If these slow journeys through curious truths help ease the mind toward rest, a subscription might bring more of them your way. The story of why we fall and why we never stop begins with a simple question that took centuries to ask properly. And the answer, when it finally came, changed everything we thought we knew about the ground beneath us. Let us begin there. You are lying still now, perhaps in your bed, perhaps on a couch, perhaps somewhere soft and quiet where the day has finally agreed to leave you alone. Your body feels heavy against the mattress or the cushions, pressed down by something you have known your whole life, something so constant that you rarely think to name it. You feel motionless. You feel at rest. And in the most practical sense, the sense that matters for sleeping and breathing and letting your thoughts grow soft around the edges, you are indeed at rest. But there is a secret you keep from yourself, a secret your body has been keeping from your conscious mind since the moment you were born, and it is simply this: you have never once been still. Right now, in this very moment of apparent quiet, you are moving faster than any vehicle you have ever ridden in, faster than any aircraft, faster than anything your ancestors could have imagined when they looked up at the night sky and wondered about the nature of the heavens. The Earth beneath you is rotating, spinning on its axis as it has done for more than 4 billion years. And if you happen to be lying somewhere near the equator, this rotation is carrying you eastward at approximately 1,670 kilometers per hour. That is faster than the speed of sound in air, faster than a bullet fired from many types of rifles. And yet you feel nothing, you hear nothing. You experience no wind rushing past your ears, no sense of motion whatsoever. The rotation is so smooth, so constant, so perfectly uniform that your body has no way of detecting it, no reason to inform your conscious mind that anything at all is happening. But the rotation is only the beginning, only the smallest of the motions that are carrying you through the cosmos at this very moment. The Earth itself is not stationary in space. It is falling in a great curved path around the Sun, held in its orbit by the same force that presses you into your bed right now, the same gentle and persistent pull that we call gravity. This orbital motion carries you and everyone you have ever known and everything that has ever happened on this planet at a speed of roughly 107,000 kilometers per hour. In the time it takes you to draw a single slow breath, you will have traveled perhaps 30 kilometers through space, though you will feel none of it, though your tea will not slosh in its cup, though the air around you will remain perfectly still. And even this tremendous orbital velocity is merely a small part of the larger motion that is carrying you onward, ever onward, through the darkness between the stars. Our entire solar system, the Sun and all its planets and moons and asteroids and comets, is itself moving, orbiting around the center of our galaxy, the Milky Way. at a speed that dwarfs our motion around the Sun. We are traveling at approximately 828,000 kilometers per hour around a galactic center that lies some 26,000 light-years away. A journey so vast that even at this incomprehensible speed, it will take our solar system roughly 230 million years to complete a single orbit. Dinosaurs walked the Earth the last time we were in this part of the galaxy. They too were hurtling through space at this same tremendous velocity, and they too felt nothing, sensed nothing, went about their dinosaur lives entirely unaware of the cosmic journey they were taking. But even this is not the end of the motion, not the final layer of velocity that is carrying you through the universe as you lie here in the quiet darkness. Our entire galaxy, the Milky Way, with its hundreds of billions of stars, is itself moving through space, drawn towards something that astronomers have named the Great Attractor, a region of space where the mass of thousands of galaxies pulls on everything nearby with a gentle but persistent gravitational force. We are falling toward this distant concentration of matter at a speed of approximately 2.2 million kilometers per hour, a velocity so enormous that it seems almost meaningless to speak of it in human terms. And yet you feel nothing, you sense nothing. You lie here in your bed, feeling perfectly, wonderfully still. This is the secret you keep from yourself, the secret that your body and your senses conspire to hide from your conscious awareness. You are always moving, always falling, always hurtling through space at velocities that would be terrifying if you could perceive them. And yet you feel absolutely nothing at all. The cup of water on your bedside table does not tip over. The pictures on your walls do not rattle. Your breath does not catch in your throat with the sensation of speed. Everything feels calm and quiet and motionless, exactly as it should feel for sleeping, exactly as it has always felt since the first moment you opened your eyes in this world. There was a man who thought deeply about this paradox, about the strange relationship between motion and sensation, between falling and the feeling of falling. His name was Albert Einstein, and in the year 1907, while working in a patent office in Bern, Switzerland, he had what he later called the happiest thought of his life. It was not a thought about love or success or any of the things we usually associate with happiness. It was a thought about gravity, about falling, about what it would feel like to fall freely through space without anything to stop you or slow you down. Einstein imagined a man falling from the roof of a building, and he realized something profound and strange and wonderful about this unfortunate scenario. The falling man, during those brief moments of his descent, would not feel his own weight. He would not feel the tug of gravity pulling him down. He would feel, in fact, weightless, as though gravity had momentarily ceased to exist, as though he were floating in empty space, far from any planet or star. This is a peculiar thing to notice, and an even more peculiar thing to call the happiest thought of your life. But Einstein understood that this simple observation contained within it a deep truth about the nature of gravity itself. The falling man does not feel gravity because he is moving with gravity, because he is following exactly the path that gravity wants him to follow, because he and gravity are no longer in opposition, but are instead working together in perfect harmony. This is very different from standing on solid ground, where the floor pushes up against your feet with exactly enough force to counteract gravity's downward pull, where you feel squeezed between two forces, where your body registers the sensation of weight pressing down upon your bones. When you fall freely, there is no floor to push back, no resistance to create the sensation of weight, and so you feel nothing at all, nothing but a peaceful floating sensation that is indistinguishable from weightlessness. Einstein developed this observation into what he called the equivalence principle, which states that the experience of gravity and the experience of acceleration are fundamentally identical, that there is no experiment you can perform in a sealed room that will tell you whether you are being pulled down by gravity or being accelerated upward by a rocket engine. Both feel exactly the same. Both produce the same weight pressing on your body. And conversely, free fall and floating in empty space also feel exactly the same, both producing that same sensation of weightlessness, that same absence of any force pressing upon you. This principle has profound implications for our understanding of the universe. But for our purposes here, lying quietly in the darkness, it helps explain something that astronauts experience every day aboard the International Space Station. You may have seen photographs or videos of astronauts floating inside the station, drifting through the air with their hair standing up and water forming perfect spheres that shimmer and dance in the cabin lights. It is natural to assume, looking at these images, that the astronauts are floating because there is no gravity in space, because they have escaped beyond the reach of Earth's gravitational pull and are now free from its influence. But this is not what is happening at all. The International Space Station orbits at an altitude of roughly 400 kilometers above the Earth's surface, and at that height, gravity is still very much present. It is only about 10% weaker than the gravity you feel right now, lying in your bed. The astronauts are not floating because gravity has let them go. They are floating because they are falling around the Earth at a speed of approximately 28,000 kilometers per hour, falling along a curved path that constantly misses the Earth's surface because their sideways motion carries them past the horizon as fast as gravity pulls them down. The astronauts are falling, and the space station is falling, and the air inside the station is falling, and the water and the food and the scientific equipment are all falling together, all following the same curved path through space, all moving in perfect unison under the influence of gravity. And because everything is falling together, because there is nothing to resist the fall, because there is no floor rising up to meet them and push back against their weight, the astronauts feel weightless. They feel as though gravity does not exist. They experience that same peaceful floating sensation that Einstein imagined the man falling from the roof would feel, that same absence of any force pressing upon the body. This is the hidden truth about gravity that you carry with you through every moment of your life. Gravity never actually lets go. It reaches out across the vast emptiness of space, connecting every particle of matter to every other particle of matter, growing weaker with distance but never quite vanishing entirely. The Moon feels Earth's gravity, which is why it orbits our planet rather than drifting off into space. The Earth feels the Sun's gravity, which is why we orbit our star rather than wandering alone through the darkness. The Sun feels the gravity of the galactic center, and our galaxy feels the gravity of the great attractor. And on it goes, an endless web of gravitational connections linking everything in the universe to everything else. Gravity never lets go, but it becomes invisible, becomes undetectable, when everything falls together. This is the secret that your body keeps from your conscious mind. The reason you can lie here feeling perfectly still while hurtling through space at millions of kilometers per hour. You are falling, and the earth is falling, and the air around you is falling, and everything you can see and touch and hear is falling along with you. And because you are all falling together, you feel nothing at all. What does it mean, then, that falling feels like nothing? What does it tell us about the nature of motion and rest? About the strange relationship between our sensations and the underlying reality of the physical world? These are questions worth holding gently in your mind as you drift toward sleep. Not urgently, not anxiously, but softly, the way you might hold a smooth stone you found by a river, turning it over in your thoughts and noticing its weight and texture without needing to understand exactly where it came from or how it got there. For now, it is enough to know that you are moving, that you have always been moving, that you will continue moving long after you fall asleep and your breathing grows slow and steady. It is enough to know that the stillness you feel is not a lie exactly, but a kind of translation, a way that your body has found to make sense of a universe that is far stranger and more wonderful than our everyday senses can perceive. You are falling through space at this very moment, falling along with everyone and everything you love, falling in a motion so smooth and so constant that it has become indistinguishable from perfect rest. And perhaps there is something comforting in this thought, something peaceful about knowing that falling, when it is done properly, when nothing resists it and nothing interrupts it, feels exactly like floating, feels exactly like stillness, feels exactly like lying in your bed at the end of a long day with nothing to do but breathe and let your thoughts grow soft around the edges. Gravity is holding you gently, as it has always held you, as it will continue to hold you through the night and into the morning that follows. You are falling, and you are safe, and you feel nothing at all. Long before anyone thought to write equations in chalk, or to measure the world with instruments of brass and glass, people simply watched things fall. They watched rain descend from clouds, watched fruit drop heavily from branches, watched the slow, inevitable tumble of leaves in autumn and the sudden startling plunge of a bird struck mid-flight. Falling was everywhere, constant as breathing, and yet, for all its ordinariness, it carried a quiet strangeness that settled into the minds of those who paused to consider it. Why should things move downward at all? One might wonder while sitting beneath an olive tree in the afternoon heat. Why not sideways, or upward, or in gentle spirals like smoke rising from a fire? The answer seemed obvious until you tried to speak it aloud, and then it dissolved into something murkier, something that required more words than you had expected, and perhaps more understanding than anyone in those early centuries possessed. The ancient Greeks, who found philosophy in everything from the movement of stars to the shape of a drinking vessel, naturally turned their attention to this question of falling. Among them, in the 4th century before the Common Era, there lived a man named Aristotle, a student of Plato and tutor to Alexander, whose mind ranged across subjects so numerous that listing them would carry us far from our gentle path tonight. Aristotle watched objects fall, as others had watched before him, But he also attempted something rather ambitious, which was to explain falling as part of a grand unified understanding of everything that exists. In his view, the universe was organized according to a deep and fundamental order, with the Earth sitting motionless at its very center, fixed and patient while the heavens wheeled around it in crystalline spheres. This was not arrogance about humanity's importance, not exactly, but rather a logical conclusion based on careful observation, or what seemed like careful observation at the time. Heavy things, Aristotle reasoned, fall because they are seeking their natural place, and the natural place of heavy things is the center of the universe, which happens to be where we stand. Light things, like flame and smoke, rise upward because their nature draws them toward the celestial realm above. Everything has a home to which it yearns to return, and motion is simply the process of going home. From this framework, it seemed perfectly sensible to Aristotle that heavier objects should fall faster than lighter ones. After all, if a stone contains more of the earthy element than a feather does, then surely its yearning for the center must be proportionally stronger, its rush toward home more urgent. Drop a large rock and a small pebble from the same height, Aristotle suggested, and the rock will strike the ground first, arriving with a satisfaction that its lighter companion cannot quite match. This idea persisted for nearly 2,000 years, passed down through generations of scholars who had enormous respect for Aristotle's authority and rather less inclination to climb towers and drop things to see whether he had been correct. There is something almost soothing about this, when you think of it in the quiet darkness, the way human knowledge sometimes rests peacefully undisturbed for centuries, not because people lacked curiosity, but because the existing explanation seemed sufficient, seemed complete, seemed to fit the world as they experienced it. And so the centuries turned, slowly as they do, through the rise and fall of Rome, through the long medieval twilight, through the gradual reawakening of European inquiry that we sometimes call the Renaissance. In the Italian peninsula during the late 16th century, there was born a man who would look at falling objects with fresh eyes and find that Aristotle, for all his brilliance, had been mistaken on this particular point. His name was Galileo Galilei, and he came from Pisa, a city known then and now for its leaning tower, which tilts so distinctly that it seems perpetually on the verge of falling itself, though it never quite does. There is a famous story, one you may have heard whispered in schoolrooms or read in books with colorful illustrations, about Galileo climbing that leaning tower with objects of different weights and dropping them simultaneously before a crowd of astonished onlookers. The heavy ball and the light ball struck the ground at the same moment. The story goes, and Aristotle's ancient theory came crashing down along with them. It is a wonderful tale, vivid and satisfying, with a clear hero and a clear revelation, but it is almost certainly not true, or at least not true in the dramatic way it is usually told. No reliable contemporary account describes this public demonstration, and historians who have sifted through the records of Galileo's life find only later retellings, embellished and polished like a stone tumbled smooth in a stream. This need not trouble us over much. However, because what Galileo actually did, in the quieter setting of his workshop in Padua around the year 1604, was perhaps more remarkable and certainly more methodical than any single theatrical drop from a tower. Unable to measure the swift passage of a falling object with the crude timekeeping devices available to him, Galileo did something clever, something that reveals the patient ingenuity of a true experimenter. He slowed falling down. He built inclined planes, smooth boards set at shallow angles, and rolled polished bronze balls along their lengths. A ball rolling down a gentle slope is, in a sense, falling very slowly, stretched out over time and distance so that a human observer can watch and measure and count. Galileo timed these rolls using a water clock, letting water drip steadily into a container and weighing it afterward to determine elapsed time. It was a tedious process, requiring many repetitions, many adjustments, many hours of careful attention in a workshop lit by candles and daylight through dusty windows. But from this patience emerged something extraordinary, a pattern so clean and so consistent that it could only be a law of nature rather than a quirk of particular objects. Galileo found that all objects, regardless of their weight, accelerate at the same rate when they fall. Heavy or light, dense or hollow, gold or lead or wood or stone. They all gain speed in precisely the same way, adding roughly 9.8 meters per second to their velocity with every second of falling. The number itself is less important than the universality it represents, the quiet democracy of falling that makes no distinction between the mighty and the meager. This was a profound shift in understanding, though its full implications would take time to unfold. Galileo pondered falling in other ways too, imagining experiments that could not easily be performed, but which illuminated the logic of motion through pure thought. Consider, he suggested, a ship sailing steadily across a calm sea, moving forward at a constant pace. If you climb the mast and drop a stone, where will it land? Aristotle's followers might have expected it to fall behind the ship, since the ship moves forward while the stone merely falls, leaving the stone to splash into the water some distance back from where it was released. But this is not what happens, as any sailor who has dropped things from rigging could attest. The stone falls straight down relative to the ship and lands at the base of the mast, just as it would if the ship were standing still. This is because the stone, before it was dropped, was already moving forward along with the ship, and it carries that forward motion with it as it falls. The falling and the forward motion combine, but they do not interfere with each other, each proceeding independently as though the other did not exist. This principle, sometimes called Galilean relativity, would echo through physics for centuries to come, finding its fullest expression much later in the work of another thinker whom we shall meet in due time. While Galileo labored in Padua, experimenting with his inclined planes and writing dialogues that would eventually attract the dangerous attention of the Church, another man worked in the cold northern reaches of Europe, tracing a different path toward the same great questions. Johannes Kepler, born in the German lands of the Holy Roman Empire, had devoted his life to the motion of the planets, those wandering lights that drift slowly against the fixed stars, sometimes looping backward in their courses in a way that had puzzled astronomers since antiquity. Using the meticulous observations of his predecessor, Tycho Brahe, who had spent decades measuring planetary positions with unprecedented accuracy. Kepler calculated and recalculated, trying formula after formula, searching for the hidden shape of celestial motion. The work was exhausting and often discouraging, filled with false starts and abandoned theories, with numbers that almost fit and then stubbornly refused to fit completely. But in 1609, in a book titled Astronomia Nova, Kepler announced what he had found. The planets do not move in perfect circles, as had been assumed for thousands of years. They move in ellipses, those elongated ovals that you might draw by pinning a loop of string at 2 points and tracing around them with a pencil. The Sun sits not at the center of these ellipses, but at one focus, slightly off to the side, and the planets sweep through their orbits at varying speeds, moving faster when closer to the Sun and slower when farther away. Kepler's laws were precise and beautiful, matching Tycho's observations with an accuracy that no previous theory had achieved. And yet, for all their elegance, they left a crucial question unanswered. Why should planets move in ellipses? What force or principle compels them to trace these particular curves rather than some other shape entirely? Kepler himself suspected that some kind of influence emanated from the Sun, pushing or pulling the planets along their paths, but he could not formulate this suspicion into a clear mathematical law. He sensed the presence of something he could not name, a hidden mechanism that governed the heavens just as surely as it governed the fall of stones on Earth. The connection between these two realms, the celestial and the terrestrial, remained tantalizingly out of reach. So the 17th century advanced, carrying with it these two great insights: Galileo's discovery of uniform acceleration and Kepler's laws of elliptical orbits, each profound on its own and yet incomplete without the other. They were like two halves of a key, waiting for someone to fit them together and unlock the deeper truth they implied. The stage was set, the props arranged, and in the fullness of time another mind would arise to complete the work. But we need not rush toward that moment tonight. Instead, let us pause to consider Galileo himself in his final years, for there is a tenderness in this part of the story that deserves a quiet telling. In 1633, at the age of 69, Galileo was called before the Inquisition in Rome and forced to recant his support for the Copernican view that the Earth moves around the Sun. He spent the remainder of his life under house arrest at his villa near Florence, forbidden to travel, forbidden to publish, watched carefully by authorities who feared what his ideas might do to the settled order of things. But even in confinement, even under the weight of official condemnation, Galileo continued to think and to write, setting down his conclusions about motion and mechanics in a book that would be smuggled out of Italy and published in the Netherlands, where the Inquisition's reach did not extend. What makes these final years particularly poignant, and perhaps particularly relevant to our nocturnal reflections on falling and motion, is that Galileo spent them increasingly in darkness. For years he had observed the heavens through his telescope, that instrument he had not invented but had refined and pointed upward to such startling effect. He had seen the craters of the moon, the moons of Jupiter, the phases of Venus, the multitude of stars in the Milky Way. But he had also, on more occasions than wisdom would advise, turned his telescope toward the Sun, observing the dark spots that drifted across its brilliant face. The damage accumulated slowly, as such damage often does, and by 1637, Galileo was completely blind. The man who had seen farther into the heavens than any before him could no longer see the hand held before his face, and yet he did not stop thinking about motion. In letters dictated to assistants, in conversations with disciples who visited his villa, in the quiet hours of sleepless nights, Galileo continued to ponder the nature of falling, the behavior of pendulums, the strange and beautiful regularity of accelerating objects. He had given the world a number, 9.8 meters per second squared, and a principle that all objects fall equally regardless of their weight, and a method, the careful experimental approach that would eventually transform natural philosophy into what we now call science. These gifts remained even as his sight departed, carried forward by students and correspondents and readers of his smuggled books, waiting to be combined with Kepler's celestial mathematics by a mind not yet born in the darkness of his final years. One imagines Galileo might have felt a kinship with the objects he had studied, the stones and balls and pendulums that moved according to laws they could not see, responding to forces they could not understand. We are all falling, in a sense, carried along by influences we barely perceive, and perhaps there is comfort in knowing that the falling itself follows rules, that even in the absence of light there is order, that even when we cannot see the ground rushing up to meet us, the mathematics remains true and gentle and precise. So let us hold these images softly as we continue. The inclined planes of Padua, the elliptical orbit sketched in a Prague study, the blind old philosopher dictating his thoughts in a villa outside Florence. They are pieces of a larger picture, fragments waiting to be assembled, and in the next portion of our journey, we shall see how they came together at last. But for now, there is no hurry. The falling continues, steady and predictable, 9.8 meters per second, whether we are awake to witness it or drifting gently towards sleep. The stones have asked their questions, and in time, the answers will come. In the summer of 1665, a young man of 22 years left Cambridge University and returned to the quiet farmhouse where he had been born. The plague had come to England once again, spreading through London and reaching outward into the surrounding counties, and the universities had closed their doors as a precaution against the sickness. This young man, whose name was Isaac Newton, packed what books and papers he could carry and travelled the 50 miles north to Woolsthorpe Manor, a modest stone house in the rolling countryside of Lincolnshire, where his mother and her second family still lived. He took up residence in his childhood room, and there, in that unremarkable farmhouse, surrounded by apple orchards and sheep pastures, he began to think about the nature of the universe in ways that no human being had thought before. The plague years, as they came to be known, stretched on for nearly 2 years, and during that time Newton remained largely at Woolsthorpe, with little to do but read and calculate and wonder. He had no laboratory to speak of, no great library at his disposal, no colleagues with whom to discuss his ideas. He had only his own mind, a few books, the quiet of the countryside, and an extraordinary capacity for sustained concentration that bordered on the obsessive. Later in his life, Newton would look back on this period as the most intellectually productive of his entire existence, a time when the foundations of calculus, the nature of light, and the laws governing motion and gravity all began to take shape in his solitary thoughts. It was during this period, according to Newton himself, that he first began to consider seriously the force that makes things fall. The story of the apple has become so famous that it is sometimes difficult to separate the legend from the history. But we do have a reasonably reliable account of what actually occurred. In 1726, when Newton was a very old man of 83, he received a visit from a younger scholar named William Stukely, who was writing a biography of the great scientist. Stukely recorded their conversation in his notes, describing how they had taken tea together in the garden beneath some apple trees, and how Newton had fallen into a reminiscent mood. According to Stukely's account, Newton told him that he had been in just such a contemplative situation when the notion of gravitation first came into his mind. He said that it was occasioned by the fall of an apple, as he sat thinking beneath a tree. The apple did not, as the popular legend sometimes suggests, strike Newton on the head. It simply fell, as apples do, and Newton, watching it descend, found himself wondering why the apple always fell straight down, perpendicular to the ground, rather than going sideways or upward. The apple fell because the earth drew it. Newton reasoned, and there must be some drawing power in matter, some attractive force that pulled objects toward the center of the earth. But then Newton's thoughts took a remarkable turn, a leap of imagination that would change our understanding of the cosmos forever. He began to wonder about the moon, that pale companion that circles our world in its endless orbit, and he asked himself a question that seems simple only in retrospect. If the earth draws the apple toward itself, does it also draw the moon? And if so, why does the moon not fall to the earth as the apple does? Why does the moon remain suspended in the sky, circling around us night after night, year after year, century after century, without ever crashing down? The answer that Newton arrived at was both elegant and profound. The moon, he realized, is falling toward the earth constantly. It is falling at every moment, just as the apple falls, pulled by the same attractive force that operates on all matter everywhere. But the moon is also moving sideways, traveling through space at considerable speed. And this sideways motion carries it around the curve of the earth, even as it falls toward the earth's center. The moon is perpetually falling and perpetually missing, caught in an endless dance of attraction and motion that we call an orbit. If you could somehow stop the moon's sideways movement, it would indeed plummet toward us, accelerating as it came, just as the apple accelerates toward the ground. But because it moves sideways so swiftly, the surface of the earth curves away beneath it at precisely the rate that it falls. And so the moon remains forever falling without ever arriving. This insight, that orbital motion is simply falling with enough sideways speed to keep missing the ground, was genuinely revolutionary. It meant that the heavens and the earth were not separate realms governed by different laws, as people had believed for thousands of years. The same force that pulled the apple from the tree also held the moon in its orbit, and presumably held the planets in their paths around the sun, and perhaps governed the motions of all bodies everywhere in the universe. The force we feel as weight, the gentle pressure that holds us to our chairs, was the same force that shaped the architecture of the solar system. Newton called this force gravity, from the Latin word gravitas, meaning heaviness, and he set about trying to understand its mathematical properties. One of the first things Newton wanted to know was how the strength of gravity changed with distance. It seemed obvious that gravity must weaken as one moved farther from the center of the Earth. But by what rule did it weaken? Newton reasoned that if gravity spread outward from a body like light from a candle, then its intensity should diminish according to a specific geometric pattern. Imagine a candle flame sending light in all directions. At a distance of 1 meter, that light is spread across the surface of a sphere with a certain area. At a distance of 2 meters, the same amount of light must cover a sphere with 4 times the area, because the surface area of a sphere increases with the square of its radius. Therefore, the intensity of light at 2 meters is only 1/4 of what it was at 1 meter. Newton proposed that gravity follows the same pattern, a relationship we now call the inverse square law. If you double your distance from the center of the Earth, the gravitational pull you feel becomes not half as strong, but 1/4 as strong. If you triple your distance, the pull becomes 1/9 as strong. If you move 10 times farther away, gravity weakens to 1/100th of its former value. This mathematical relationship, simple yet precise, allowed Newton to make calculations about the motion of the moon and to test whether his ideas matched the observed facts. The moon orbits the Earth at an average distance of about 384,000 kilometers, which is roughly 60 times the radius of the Earth itself. According to the inverse square law, gravity at the moon's distance should be weaker than gravity at the Earth's surface by a factor of 60 squared, which is 3,600. An object that would fall about 5 meters in the first second near the Earth's surface should therefore fall only about 1.4 millimeters in the first second at the moon's distance. Newton calculated this figure and compared it to the actual motion of the moon in its orbit, and found that the numbers agreed remarkably well. The moon was indeed falling toward the Earth at almost exactly the rate predicted by the inverse square law of gravity. This confirmation gave Newton confidence that he was on the right track, but he did not immediately publish his findings. He was a secretive man, prone to long periods of isolation and reluctant to share his work with others. He had also encountered some mathematical difficulties in his calculations, particularly concerning whether it was legitimate to treat the entire Earth as if all its mass were concentrated at a single point at its center. This problem troubled him for years, and it was not until he had developed more sophisticated mathematical tools that he was able to resolve it to his satisfaction. 2 decades passed before Newton finally organized his ideas about gravity and motion into a coherent system. The impetus came from an unexpected source: a conversation with the astronomer Edmund Halley in 1684. Halley had been discussing the motions of the planets with other members of the Royal Society, and a question had arisen that none of them could answer. If the planets were held in their orbits by some attractive force from the sun, and if that force followed an inverse square law, what shape would the orbits take? Halley travelled to Cambridge to ask Newton this question, and Newton replied almost immediately that the orbits would be ellipses. He knew this. he said, because he had calculated it years ago. When Halley asked to see the calculation, Newton could not find it among his papers, but he promised to work it out again and send it along. What Newton sent to Halley a few months later was far more than a simple calculation. It was the beginning of a complete mathematical description of motion and gravity, a work that would eventually grow into one of the most important scientific books ever written. Halley recognized its significance at once, and he urged Newton to expand and publish his findings. When the Royal Society proved unable to fund the publication, Halley paid for it himself, covering the costs of printing from his own modest income. The book appeared in 1687 under the title Philosophiae Naturalis Principia Mathematica, which translates as Mathematical Principles of Natural Philosophy, though it is usually known simply as the Principia. In the Principia, Newton presented his 3 laws of motion and his universal law of gravitation, showing how these principles could explain not only the fall of apples and the orbit of the moon, but also the tides of the oceans, the paths of comets, the shape of the Earth itself, and countless other phenomena. The mathematical precision of his work was unprecedented. He could calculate exactly how fast a planet would move at any point in its orbit, how the gravitational pull of Jupiter perturbed the orbit of Saturn, how the moon's attraction raised the waters of the sea. The universe, it seemed, operated like a vast and intricate clockwork, governed by mathematical laws that could be written down and understood. Yet, for all the power and precision of his theory, Newton was troubled by something he could not explain. He could describe gravity perfectly, could calculate its effects to extraordinary accuracy, but he had no idea what gravity actually was. He could not say what caused masses to attract one another, or how the Earth could reach across 384,000 kilometers of empty space to pull on the moon. This was not a minor gap in his understanding, but a profound philosophical mystery at the heart of his entire system. Newton's contemporaries raised this objection repeatedly. How could the sun exert a force on the Earth without touching it? What medium carried this influence across the void? The dominant scientific philosophy of the time, associated with the French thinker René Descartes, held that all physical effects must be transmitted through direct contact, through particles pushing against particles in an unbroken chain. Action at a distance, the ability of one body to affect another without any intervening substance, seemed almost magical, a throwback to the occult forces that the new science was supposed to have banished. Newton felt the force of this criticism keenly, and he admitted freely that he did not have an answer. In the second edition of the Principia, he included a famous passage addressing this very issue. He wrote that he had not been able to discover the cause of the properties of gravity from phenomena, and that he would feign no hypotheses. Whatever is not deduced from the phenomena, he wrote, is to be called a hypothesis, and hypotheses have no place in experimental philosophy. This phrase, "I feign no hypotheses," became one of the most quoted statements in the history of science, an expression of Newton's commitment to describing what he could observe and measure, even when he could not explain the underlying mechanism. But privately, Newton found the implications of his own theory deeply unsettling. According to his mathematics, gravity acted instantaneously across any distance. When the sun moved, The Earth felt the change in gravitational pull at the very same moment, without any delay, no matter how far apart they were. This seemed to violate basic intuitions about cause and effect. How could an influence travel infinitely fast? How could the sun reach out and touch the Earth across 93 million miles of nothing in literally no time at all? Newton called this action at a distance and described it as so great an absurdity that he believed no man who had a competent faculty of thinking could ever fall into it. Yet fall into it he had, for his equations demanded it, and his equations worked. The predictions matched the observations with uncanny precision. And so, Newton was forced to accept a theory whose philosophical foundations he himself found troubling. Gravity, in Newton's formulation, was a kind of invisible hand reaching across the cosmos, connecting every particle of matter to every other particle, acting everywhere at once, instantaneously, through the pure emptiness of space. It was, to use a word that would later become famous in a different context, a spooky kind of action, a ghostly influence that seemed to operate by magic even as it obeyed strict mathematical laws. This mystery sat at the center of physics for more than 200 years. Newton's equations were used to predict the motions of planets and moons, to aim cannonballs and design bridges, to navigate ships and launch the first rockets. They were among the most successful scientific theories ever devised, confirmed again and again by observation and experiment. Yet the fundamental question remained unanswered. What is gravity? How does it work? By what mechanism does the Earth reach out and pull the Moon toward itself across the silent emptiness of space? Generations of scientists accepted Newton's equations while setting aside the deeper question, treating gravity as a brute fact of nature that needed no further explanation. The inverse square law worked, and that was enough for most practical purposes. But the mystery never quite went away. It lingered in the background, a gentle puzzle waiting patiently for someone to come along and see the universe in a new way. That someone would not appear for another 2 centuries, and when he did, his explanation would be stranger and more beautiful than anything Newton could have imagined. Let us now turn our attention to one of the most extraordinary reimaginings of the physical world ever conceived by the human mind. A reconceptualization so profound and so quietly revolutionary that it transformed our understanding not merely of gravity, but of the very nature of space and time themselves. And I think you will find, as you settle more deeply into your resting place, that this particular story has a curious and rather comforting quality to it. Because what Einstein proposed in 1915 was something that might, at first hearing, seem almost more restful than the older Newtonian picture, in the sense that you are not, in fact, being pulled downward by any invisible force at all, but are rather simply following the most natural path available to you through a universe whose geometry has been gently curved by the presence of mass and energy. And there is something rather peaceful in that notion, the idea that you are not struggling against some relentless tug, but are instead doing what any object would do when left to its own devices in curved spacetime, which is to say, you are taking the straightest possible route through a landscape that happens to be bent. To understand how Einstein arrived at this remarkable picture, we must return to the early years of the 20th century. when he was working at the patent office in Bern, Switzerland, and thinking very deeply about the nature of acceleration and gravitation. And it was during this period that he experienced what he would later describe as the happiest thought of his life. A thought experiment so elegant in its simplicity that it would eventually unlock the entire theory of general relativity. And this thought experiment involved imagining a person enclosed within an elevator, or a lift, as we might say, with no windows and no means of seeing the outside world. And Einstein asked himself what such a person would experience under two quite different circumstances. Firstly, if the elevator were sitting stationary on the surface of the Earth, with gravity pulling everything downward in the usual way. And secondly, if the elevator were out in deep space, far from any gravitating body, but being accelerated upward by some rocket engine attached to its base. And the remarkable conclusion that Einstein reached was that the person inside the elevator would have absolutely no way of distinguishing between these two situations, because in both cases they would feel their feet pressed against the floor with exactly the same sensation, and any object they released from their hand would appear to fall toward the floor in exactly the same manner. And this equivalence, this perfect indistinguishability between gravitational effects and the effects of acceleration, became the foundation upon which the entire edifice of general relativity would be constructed. Einstein called this insight the equivalence principle, and he spent the next several years working out its implications, struggling with mathematics that proved far more demanding than anything he had encountered before. And it was during this period that he turned to an old friend from his student days at the Polytechnic in Zurich, a mathematician named Marcel Grossmann, who had once helped Einstein by lending him his lecture notes when Einstein had been rather negligent about attending classes. And now Grossmann would help him again in a far more consequential way, by introducing him to a branch of mathematics that had been developed decades earlier by the German mathematician Bernhard Riemann, a mathematics of curved spaces and non-Euclidean geometry that would prove to be precisely the tool Einstein needed to describe his new vision of gravity. And together, Einstein and Grossmann labored over the tensor calculus and the metric tensor and all the formidable apparatus of Riemannian geometry. And although the mathematics was often frustrating and the path forward was not always clear, Einstein persisted because he felt certain that the equivalence principle was pointing towards something true and deep about the nature of reality. What emerged from these years of labor was a theory in which spacetime itself, the four-dimensional fabric woven from 3 dimensions of space and 1 of time, was not a fixed and rigid stage upon which events unfold, but was rather a dynamic and flexible medium that could be warped and curved by the presence of mass and energy. And in this picture, the planets do not orbit the Sun because the Sun is pulling them inward with some mysterious force that acts across empty space, but rather because the Sun, being massive, creates a curvature in the space-time around it, a kind of gentle depression or warping of the geometry, and the planets simply follow the straightest possible paths through this curved landscape. Paths that mathematicians call geodesics. And because the geometry is curved, these straightest possible paths happen to be closed orbits rather than straight lines. And so the Earth goes round and round the Sun, not because it is being tugged, but because it is doing the most natural thing it can do in the curved spacetime created by the Sun's mass. And there is something rather lovely in this image. I think The notion that celestial bodies are not locked in some perpetual struggle against invisible chains, but are rather gliding along the gentlest available contours of a curved universe, taking the path of least resistance through bent geometry. The same principle applies to you, lying there so peacefully in the grip of what you have always called gravity. Because the Earth beneath you is massive enough to curve the space-time in your vicinity, and your body, left to its own devices, would naturally follow a geodesic path through this curved region, a path that would carry you toward the center of the Earth. And the only reason you are not following this path, the only reason you are remaining stationary relative to the Earth's surface, is that the ground beneath you is exerting an upward force that prevents you from following your natural geodesic trajectory. And this is perhaps the most counterintuitive aspect of Einstein's vision: the realization that what you feel as weight, that sensation of heaviness pressing you down into your mattress, is not the result of gravity pulling you downward, but is rather the result of the ground pushing you upward, preventing you from falling freely along the curved path that space-time has prepared for you. And if the floor were suddenly to vanish and you were to fall freely toward the center of the Earth, you would feel weightless during that fall. Just as astronauts feel weightless when their space station falls freely in orbit around the Earth, because in free fall you are following your natural geodesic and there is no force acting upon you, and the only reason you ever feel weight at all is that something, whether a floor or a chair or a mattress, is pushing against you and preventing you from following that geodesic path. Now, this was all very well as a theoretical framework, a beautiful and mathematically elegant reimagining of gravity. But science requires more than elegance. It requires predictions that can be tested against the actual behavior of the physical world. And Einstein knew that his theory would not be taken seriously until it could be confirmed by observation. And so he worked out several predictions that differed from what Newton's theory would have predicted. And one of the most accessible of these predictions concerned the bending of light as it passed near a massive body like the Sun. Because if space-time is curved by mass, then light, which travels along geodesics through space-time, should follow curved paths when passing through regions where space-time is warped. And Einstein calculated that a ray of starlight grazing the edge of the Sun should be deflected by an angle of approximately 1.75 arc-seconds, which is a very small angle indeed, roughly equivalent to the apparent width of a human hair viewed from a distance of about 10 meters. And this prediction differed from what Newton's theory would have suggested, because even in Newton's framework, one could calculate a bending of light by treating light as if it were made of particles affected by gravity. But Newton's calculation yielded only half the deflection that Einstein predicted. And so here was a clear observational test that could distinguish between the two theories. The difficulty was that the stars whose light would pass close enough to the Sun to be measurably deflected are normally invisible during the day, overwhelmed by the brilliance of the Sun itself. And so the only opportunity to observe this effect would be during a total solar eclipse, when the Moon blocks the Sun's disk and allows the nearby stars to become visible for a few precious minutes. And so astronomers began planning expeditions to observe the next suitable eclipse. But the First World War intervened and made international scientific expeditions extremely difficult. And it was not until 1919, after the war had ended, that the British astronomer Arthur Eddington was able to organize 2 expeditions to observe the total solar eclipse of May 29th of that year. One expedition traveling to the island of Principe off the western coast of Africa, and the other to the town of Sobral in northeastern Brazil, and Eddington himself accompanied the Principe expedition, setting up his telescopes and photographic equipment on that small island in the Gulf of Guinea and waiting anxiously for the day of the eclipse to arrive. The weather on Principe was not ideal, with clouds and rain threatening the observations, but during the totality there were sufficient breaks in the clouds to allow some photographs to be taken, and the expedition at Sobral enjoyed clearer skies. And when the photographic plates were developed and carefully measured, comparing the apparent positions of stars near the Sun during the eclipse with their normal positions when the Sun was elsewhere in the sky, the results indicated a deflection that matched Einstein's prediction rather than Newton's. And the announcement of these results at a joint meeting of the Royal Society and the Royal Astronomical Society in London in November of 1919 created a sensation, with newspapers around the world carrying headlines declaring that Newton had been overthrown, that a new theory of the universe had been confirmed, and Einstein, who had been relatively unknown outside scientific circles, became overnight a figure of worldwide celebrity. And although subsequent analyses have suggested that Eddington's measurements were perhaps not quite as definitive as they were portrayed at the time, the basic result has been confirmed many times since with far greater precision. And there is no longer any doubt that light does indeed bend when passing through the curved space-time near a massive body, bending by precisely the amount that Einstein's theory predicts. Another prediction of general relativity that has since been confirmed with extraordinary precision concerns the behavior of clocks in gravitational fields. Because Einstein's theory implies that time itself runs at different rates depending on the curvature of space-time, which is to say, depending on how deep within a gravitational field you happen to be, and specifically, clocks that are further from a gravitating body, where space-time is less curved, should run slightly faster than clocks that are closer to the body, where space-time is more strongly curved. And this effect, known as gravitational time dilation, is extremely small under ordinary circumstances. But it is not negligible when it comes to the Global Positioning System satellites that orbit the Earth at an altitude of approximately 20,000 kilometers, because those satellites carry atomic clocks that must be extraordinarily precise in order for the GPS system to function correctly, and at their orbital altitude, where the Earth's gravitational field is weaker than at the surface. Those clocks run faster than identical clocks on the ground by approximately 38 microseconds per day, which may sound like a trivially small difference, but which would accumulate to produce positioning errors of many kilometers if it were not corrected for. And so the GPS system includes relativistic corrections based on Einstein's theory, adjustments that were programmed into the system from the very beginning, because the engineers understood that without these corrections, the system would simply not work. And so, every time you use a GPS device to find your way, you are relying on the correctness of general relativity, on the truth of Einstein's insight that gravity is not a force but a curvature of space-time. And so, as you lie there feeling the gentle pressure of the mattress against your back, you might reflect that what you are experiencing is not the pull of some mysterious force reaching up from the center of the Earth, but rather the push of the ground and the mattress and the bed frame, preventing you from following your natural path through curved space-time. A path that would, if you were allowed to follow it, carry you gently toward the Earth's center in a state of perfect weightlessness. And the sensation of weight that you feel is simply the reaction to this obstruction. The price you pay for being held in place rather than falling freely. And in this sense, being at rest on the surface of the Earth is actually a kind of accelerated motion, a continuous deviation from the geodesic path that space-time has laid out for you. And true rest, in the relativistic sense, would be free fall, that serene state in which you follow the geometry of the universe without resistance, weightless and untroubled by any sensation of heaviness. And there is something gently paradoxical in this, that what feels like rest is actually a kind of resistance, and what would feel like falling is actually the most natural state of motion. And perhaps, as you drift towards sleep, you can hold this thought lightly in your mind, that you are not being pulled down, but are being pushed up, that the weight you feel is not gravity's grip, but the Earth's gentle insistence that you remain here on its surface, rather than following the curved paths that space-time has prepared. And in this way, Einstein's revolution, far from making the universe more strange and unsettling, might be seen as offering a kind of reassurance, a reminder that the universe is not full of invisible forces acting mysteriously across empty space, but is rather a smoothly curved landscape through which all things, yourself included, move along the gentlest available paths, doing nothing more than following the geometry of existence itself. In the year 1916, while the world was consumed by war and uncertainty, Albert Einstein sat with his equations and discovered something remarkable hiding within the mathematics of general relativity. He found that gravity, this curvature of space-time we have been discussing, was not always still and settled. He found that space-time itself could ripple, could shiver, could carry waves outward from violent cosmic events, much as a pond carries ripples outward from a dropped stone. These gravitational waves, as he called them, would stretch and squeeze space itself as they passed, compressing distances in one direction while elongating them in another, oscillating back and forth at frequencies determined by the events that created them. Einstein published his prediction, added it to the growing edifice of his theory, and then, in what must have been a moment of weary pragmatism, concluded that these waves would almost certainly never be detected. They were simply too faint, too subtle, too impossibly small in their effects on anything we might construct here on Earth. The universe could shiver all it liked, Einstein reasoned, and we would never know. For the better part of a century, it seemed that Einstein's pessimism was well-founded. The mathematics was clear. The prediction was robust, but the engineering required to actually sense these ripples was so far beyond contemporary capabilities that gravitational waves remained a theoretical curiosity, discussed in graduate seminars and physics conferences, but never observed directly. Physicists calculated that even the most violent events in the cosmos, the collision of black holes or the explosion of massive stars, would produce waves that, by the time they reached Earth after traveling across billions of light years, would stretch and squeeze distances by amounts smaller than the diameter of an atomic nucleus. Smaller, in fact, than the nucleus itself. Smaller than the particles that make up the nucleus. We are speaking here of measurements so delicate, so impossibly precise, that they seem to mock the very notion of human instrumentation. And yet, there were scientists who refused to accept that these waves would forever remain beyond our reach. Among them was a physicist named Rainer Weiss, who in the 1970s began to think seriously about how one might actually build a detector capable of sensing gravitational waves. Weiss, who was born in Berlin and came to America as a child, had a gift for understanding the practical challenges of precision measurement, and he began to sketch out designs for a device called a laser interferometer. The basic principle was elegant in its simplicity, even if its execution would prove almost impossibly difficult. A laser beam would be split in two, with each half sent down a long perpendicular arm. At the end of each arm, mirrors would reflect the beams back toward the center, where they would recombine. Under normal circumstances, with no gravitational wave passing through, the two beams would travel exactly the same distance and arrive back at precisely the same moment, their light waves cancelling each other out in a particular way that physicists call destructive interference. But if a gravitational wave were to pass through the detector, it would stretch one arm while squeezing the other, causing the two beams to travel slightly different distances and arrive slightly out of sync. This tiny mismatch, this minuscule difference in arrival time, would show up as a change in the interference pattern, and from that change, the passage of a gravitational wave could be inferred. The concept was straightforward, but the practice was a nightmare of engineering. The changes in arm length that Weiss and his colleagues hoped to detect were not merely small. They were preposterously, almost absurdly small. They were hoping to measure changes of less than 1/10,000th the width of a proton. To put this in perspective, which is admittedly difficult because the scales involved are so far removed from everyday experience, consider that a proton is already about 100,000 times smaller than an atom, and an atom is already so small that billions of them could fit across the width of a human hair. 1/10,000th the width of a proton is a distance so tiny that it strains the capacity of language to describe it meaningfully. And yet, this was the sensitivity required. This was the threshold that had to be crossed. At the same time that Weiss was working on the practical challenges of interferometry, a theoretical physicist named Kip Thorne was approaching the problem from the other direction. Thorne, who worked at the California Institute of Technology and had studied under the great John Archibald Wheeler, was deeply conversant with Einstein's equations and had spent years calculating what gravitational waves from various cosmic sources would actually look like how strong they would be, what frequencies they would carry, how long they would last. Thorne understood the astrophysics of the sources, the mathematics of the waves, and he became convinced that with sufficient effort and ingenuity, detection was possible. He and Weiss began to collaborate, combining theoretical insight with experimental know-how, and slowly, over many years, the dream began to take shape. The project they envisioned was called LIGO, the Laser Interferometer Gravitational Wave Observatory, and it would eventually consist of two identical detectors located thousands of kilometers apart. One detector would be built in Hanford, Washington, amid the scrublands of the Pacific Northwest. The other would be constructed in Livingston, Louisiana, surrounded by the pine forests of the Deep South. The separation was essential because any genuine gravitational wave would pass through both detectors within a fraction of a second, producing nearly identical signals in each, while local disturbances like earthquakes or traffic or even the footsteps of a wandering deer would affect only one detector at a time. By requiring that a signal appear in both detectors simultaneously, the scientists could distinguish true gravitational waves from the endless background of terrestrial noise. Each detector would consist of two perpendicular arms, each arm stretching 4 kilometers in length. Inside these arms, in vacuum chambers pumped down to a near-perfect emptiness to eliminate any interference from air molecules, laser beams would travel back and forth, bouncing between mirrors of extraordinary precision. The mirrors themselves would be suspended on sophisticated isolation systems designed to shield them from every conceivable vibration, from seismic rumbles deep in the earth to the gentle swaying caused by wind against the buildings that housed them. Every source of noise had to be identified, characterized, and either eliminated or accounted for. The team had to worry about thermal fluctuations in the mirror coatings, about the quantum uncertainty in the laser light itself, about the gravitational pull of passing clouds overhead, about the tides raised in the Earth by the distant moon. The challenges multiplied, and the project stretched across decades. In 1994, a physicist and particle accelerator expert named Barry Barish joined the project and brought with him the organizational skills and management experience necessary to transform LIGO from a promising concept into a functioning observatory. Barish had overseen large scientific collaborations before, and he understood how to coordinate the efforts of hundreds of scientists and engineers across multiple institutions and countries. Under his leadership, LIGO grew into an international endeavor, with contributions from research groups around the world, and the detectors were built, tested, refined, and rebuilt again as new technologies emerged. The first generation of LIGO detectors began operating in the early 2000s, but achieved no detections. They were sensitive, more sensitive than any instrument of their kind that had ever existed. But they were not yet sensitive enough. The gravitational waves passing through Earth, if they were passing through at all, remained hidden below the noise floor. For years, the detectors ran and recorded and found nothing, and skeptics wondered aloud whether the project was chasing a chimera, whether Einstein's pessimism had been correct all along. But the scientists pressed on. They dismantled the first-generation detectors and began constructing improved versions, with better mirrors, more powerful lasers, and more sophisticated isolation systems. The upgrade, known as Advanced LIGO, was completed in 2015, and in September of that year, the detectors were brought online for their first observing run. On the 14th of September, 2015, at approximately 9:50 in the morning, Coordinated Universal Time, both detectors recorded a signal. The signal lasted only 0.2 of a second, a brief chirp of rising frequency that swept upward before abruptly ending. The chirp was consistent with what Thorne and his colleagues had long predicted: the signature of two massive objects spiraling toward each other in the final moments before merger, their orbital frequency increasing as they drew closer together until, at last, They collided and became one. The analysis of the signal, conducted with painstaking care over the following weeks, revealed that the source was a pair of black holes, one with a mass approximately 36 times that of our Sun and the other approximately 29 times as massive, located about 1.3 billion light-years from Earth. They had been orbiting each other, locked in a gravitational embrace, for millions or perhaps billions of years, slowly losing energy to gravitational radiation and gradually spiraling inward. In those final moments, they had accelerated to nearly the speed of light, whipping around each other dozens of times per second, before merging into a single black hole with a mass of about 62 solar masses. The arithmetic reveals something startling. 36 plus 29 is 65, but the final black hole had a mass of only 62 solar masses. 3 solar masses had vanished, converted entirely into energy and carried away by the gravitational waves. 3 times the mass of our Sun transformed into ripples in the fabric of space-time. In those final 0.2 of a second, this merger released more energy than all the stars in the observable universe were producing at that moment combined. Every star in every galaxy in the vast and luminous cosmos, all of them together, were outshone by this single event. And yet, when the ripples reached Earth, after traveling for 1.3 billion years across the expanding void, they stretched and squeezed our planet by less than the width of a proton. The detectors shivered. The laser beams recorded their tiny mismatch. And we, the human beings walking on the surface of this planet, felt nothing at all. The detection was announced in February of 2016, and the response from the scientific community was immediate and jubilant. Here at last was direct evidence of gravitational waves, confirmation that space-time itself could ripple and shiver just as Einstein had predicted a century before. Here also was the first direct detection of a binary black hole system, proof that such objects existed and that they could merge in exactly the way theorists had imagined. In 2017, the Nobel Prize in Physics was awarded jointly to Rainer Weiss, Barry Barish, and Kip Thorne, honoring their roles in conceiving, building, and interpreting this remarkable instrument. Einstein's pessimism, it turned out, had been premature. We had learned to feel the shivers of the universe. But the story did not end there. On the 17th of August, 2017, LIGO and its European counterpart Virgo detected another gravitational wave signal, this one lasting much longer than the black hole merger, stretching across many seconds as the source spiraled inward more gradually. The analysis indicated that this was not a pair of black holes, but a pair of neutron stars, the dense remnants of massive stars that had exploded as supernovae long ago. Neutron stars, unlike black holes, are made of matter, and when they collide, that matter can produce light, electromagnetic radiation across the spectrum from gamma rays to radio waves. And indeed, less than 2 seconds after the gravitational wave signal arrived, orbiting telescopes detected a burst of gamma rays from the same region of the sky. In the hours and days that followed, observatories around the world turned their instruments toward the source and watched a kilonova unfold, a brilliant explosion in which heavy elements like gold and platinum were forged and scattered into space. This event, designated GW 170817, marked the birth of what scientists call multi-messenger astronomy, the ability to study cosmic events using both gravitational waves and light. For the first time, we had heard the universe and seen it simultaneously. Two fundamentally different ways of perceiving the cosmos brought together in a single observation. The implications for our understanding of neutron stars, of gamma-ray bursts, of the origin of heavy elements, were profound. But perhaps the most remarkable thing about that day in August was simply that it happened at all, that we had built instruments delicate enough to register the shivering of space-time itself. And now the gravitational waves continue to pass through us, as they have always passed through us, as they will continue to pass through us for as long as the universe endures. Every moment of every day, ripples from distant cataclysms are washing over the Earth, stretching and squeezing the space we occupy, flexing the very fabric of reality. The universe is never still. It shimmers and quivers with the echoes of events we will never see, events that happened before our planet existed, events that are happening right now in galaxies so far away that their light will not reach us for billions of years. We move through this rippling space-time, falling eternally around our sun, and the ripples pass through us, and we feel nothing. There is no sensation, no awareness, no hint that anything is happening at all. The changes are simply too small, too subtle, too far below the threshold of human perception. And yet, they are real, these ripples. They carry information about collisions and mergers and explosions at the very edge of the observable universe. They tell us stories in a language we have only just begun to understand. So here we are, falling through curved and rippling space-time, surrounded by gravity in its many guises. The Earth pulls us gently toward its center. The Sun pulls the Earth into its long looping orbit. The galaxy pulls the Sun around its vast spiraling structure. And through it all, gravitational waves pass silently by, the shivers of a universe that will never be still. It is, in the end, a rather beautiful image. This endless falling, this continuous motion, this quiet rippling that surrounds us always and touches everything and leaves no trace we can perceive. We are part of the fabric, woven into the very space-time that curves and shivers around us. And though we cannot feel it, though we go about our days without the slightest awareness of the cosmic drama unfolding at scales too large and too small for our senses to register, it is happening nonetheless. It is happening right now, as you listen to these words, as your body relaxes and your thoughts drift gently towards sleep. The universe is falling and rippling, stretching and curving, and you are part of it all, as inevitable and unremarkable and wonderful as anything that has ever been. And now we come to a place where the universe itself seems to hesitate, where the elegant mathematics we have spoken of so far begins to fray at the edges, and where the very fabric of reality refuses to behave in the orderly manner we might expect. This is the realm of the very small, the unimaginably tiny, where particles dance according to rules that gravity does not seem to understand, and where gravity, for all its cosmic grandeur, becomes strangely silent and confused. It is here, in this quiet corner of physics, that we find one of the deepest and most beautiful unsolved mysteries in all of science. A puzzle that has occupied the finest minds for nearly a century, and which remains, to this day, wonderfully and stubbornly unresolved. You see, we have spoken at some length about Einstein's general relativity, that magnificent theory which describes gravity as the curvature of space-time itself, the gentle warping of the cosmic fabric that guides planets in their orbits and bends starlight around distant suns. This theory works extraordinarily well for large things, for stars and galaxies and the expanding universe as a whole, and its predictions have been confirmed with breathtaking precision by countless experiments and observations. But there is another great pillar of modern physics, one that governs the behavior of atoms and electrons and quarks and photons. And this is the strange and counterintuitive world of quantum mechanics. In this realm, particles do not have definite positions until they are observed. Energy comes in tiny discrete packets called quanta, and the very act of measurement changes the thing being measured. Quantum mechanics is probabilistic at its heart, dealing not in certainties, but in likelihoods, not in smooth, continuous motions, but in sudden jumps and flickering uncertainties. And here is the difficulty, the gentle impasse that physicists have struggled with for generations. These two theories, general relativity and quantum mechanics, are each spectacularly successful in their own domain. Quantum mechanics describes the behavior of the electromagnetic force, the strong nuclear force that holds atomic nuclei together, and the weak nuclear force responsible for certain kinds of radioactive decay. It does so with an accuracy that is almost absurd, matching experimental results to 10 or 12 decimal places in some cases. General relativity, meanwhile, explains the motion of planets, the behavior of GPS satellites, the existence of black holes, and the expansion of the cosmos. Each theory is a masterpiece of human understanding. And yet, when we try to bring them together, when we try to apply quantum mechanics to gravity itself, the mathematics produces nonsense. The equations give infinite answers. Physical quantities that should be calculable become meaningless strings of divergent numbers, and the elegant frameworks that work so beautifully on their own refuse, quite stubbornly, to cooperate with one another. This incompatibility becomes most apparent at a particular scale, a realm of measurement so unimaginably tiny that it makes atoms look like galaxies by comparison. This is called the Planck scale, named after the German physicist Max Planck, who was one of the founders of quantum theory. The Planck length is approximately 10 to the negative 35th power meters, which is to say a decimal point followed by 34 zeros and then a 1. To give you some sense of how small this is, consider that a proton, one of the particles that makes up the nucleus of an atom, is about 10 to the negative 15 meters across. The Planck length is 20 orders of magnitude smaller than that. If you were to shrink yourself down to the size of the Planck length, a proton would be as large as the distance from Earth to the nearest star. There is also a Planck time, which is approximately 10 to the negative 44th power seconds, the time it would take light to travel one Planck length. These are not arbitrary numbers, but emerge naturally when we combine the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant, which governs quantum behavior. At this scale, Both general relativity and quantum mechanics begin to break down. The smooth, continuous space-time of Einstein's theory becomes subject to quantum fluctuations so violent that the very notion of distance and duration loses its meaning. Some physicists speak of space-time itself becoming foamy at this scale, a churning sea of virtual particles and microscopic wormholes appearing and disappearing in inconceivably brief intervals. Others suggest that space-time may not be continuous at all, but may be woven from discrete fundamental units, tiny building blocks that only appear smooth when viewed from our much larger perspective. Rather like how a photograph appears continuous to the naked eye, but reveals itself as individual pixels when examined closely enough. But we do not know for certain, because we cannot probe these scales directly. The energies required to examine the Planck scale are far beyond anything we can produce with current or foreseeable technology. And so, this realm remains hidden from us, a terra incognita at the very foundation of reality. The incompatibility between these two great theories is not merely a mathematical nuisance, but reveals itself most starkly in situations where both gravity and quantum effects should be important. One such situation occurs at the very center of a black hole. According to general relativity, when a massive star collapses at the end of its life, it can form a region of space from which nothing, not even light, can escape. At the heart of this black hole, the theory predicts, all the matter is compressed into a single point of infinite density called a singularity. But infinite density is not a physical thing that can actually exist. It is a sign, a polite but firm message from the mathematics, telling us that the theory has been pushed beyond its limits, that we are asking questions it was not designed to answer. At the singularity, general relativity breaks down completely, and we would need a quantum theory of gravity to understand what is really happening there, what the matter is actually doing, how space-time behaves when compressed to such unimaginable extremes. A similar problem arises when we consider the very beginning of the universe. According to the standard cosmological model, the universe began approximately 13.8 billion years ago in an event we call the Big Bang. If we trace the expansion of the cosmos backward in time, using the equations of general relativity, we find that the universe becomes smaller and smaller, denser and hotter, until we reach a moment when all the matter and energy in the observable universe was compressed into an infinitely small, infinitely dense point. Once again, a singularity. And once again, the mathematics is telling us that our theory is incomplete, that something else must take over at these extreme conditions, some deeper understanding that we have not yet achieved. The Big Bang singularity is not so much a moment in time as a gap in our knowledge, a place where our current physics falls silent and gestures helplessly toward mysteries it cannot resolve. And so, for decades now, theoretical physicists have been searching for a quantum theory of gravity, a framework that would reconcile general relativity with quantum mechanics, that would explain what happens at the Planck scale and inside black holes and at the birth of the universe. This search has produced some of the most creative and mathematically sophisticated work in the history of physics, but it has not yet produced a definitive answer. Several candidate theories exist, each with its own elegance and its own difficulties, and we will speak of a few of them now. in the hope that their ideas might carry you gently along towards sleep. One of the most famous approaches is called string theory, which proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings are inconceivably small, roughly the size of the Planck length, and the different ways they can vibrate correspond to different particles. Just as the different ways a violin string can vibrate produce different musical notes. In this picture, an electron is a string vibrating in one particular pattern. A quark is a string vibrating in another, and, crucially, one of the possible vibration patterns corresponds to a particle that transmits gravity. String theory, in other words, naturally includes gravity as part of its framework, which is one of the reasons it has attracted so much attention. The origins of string theory are somewhat unusual. In 1968, a young Italian physicist named Gabriele Veneziano was studying the strong nuclear force, which holds protons and neutrons together in atomic nuclei. He noticed that a particular mathematical formula, originally discovered by the 18th century mathematician Leonhard Euler for entirely different purposes, seemed to describe certain aspects of particle collisions remarkably well. It was only later that physicists realized this formula could be interpreted as describing the behavior of one-dimensional strings rather than point particles. Throughout the 1970s and 1980s, the theory was developed by many researchers, among them John Schwarz and Michael Green, who showed in 1984 that string theory could avoid certain mathematical inconsistencies that had plagued earlier attempts at quantum gravity. This result sparked what has been called the first superstring revolution, a period of intense excitement and activity in theoretical physics. But string theory comes with requirements that may seem rather surprising. For the mathematics to work out consistently, the theory requires not the 4 dimensions of space-time that we experience, 3 of space and 1 of time, but 10 or 11 dimensions in total. The extra dimensions, if they exist, must be curled up so small that we cannot detect them, compactified into tiny shapes at every point in space. These shapes can take many different forms, and each form gives rise to different physics, different particles, different forces. The number of possible shapes is staggeringly large, perhaps 10 to the 500th power or more, and each one corresponds to a different possible universe with different physical laws. This vast landscape of possibilities makes it very difficult to extract specific predictions that could be tested by experiment, and despite decades of work, no experiment has yet confirmed or refuted string theory. It remains a beautiful and mathematically rich framework, tantalizingly promising but not yet empirically verified. Another approach to quantum gravity is called loop quantum gravity, which takes a rather different path. Rather than introducing new entities like strings, loop quantum gravity attempts to apply the principles of quantum mechanics directly to general relativity itself, to the geometry of space-time. In this theory, space-time is not smooth and continuous at the smallest scales, but is woven from discrete units, something like a very fine fabric made of tiny loops. These loops are not loops in ordinary space, but rather loops of a more abstract quantity related to the gravitational field. The theory has been developed over the past several decades by physicists including Carlo Rovelli and Lee Smolin, among many others, and it offers a picture of space as fundamentally granular, with a smallest possible length and a smallest possible volume, below which the concept of space simply does not apply. In loop quantum gravity, the singularities that plague general relativity may be resolved. At the center of a black hole, or at the moment of the Big Bang, where Einstein's equations predict infinite density, the discreteness of space-time may prevent such infinities from occurring. Some calculations suggest that the Big Bang may not have been a true beginning, but rather a big bounce, a transition from a previous contracting universe to our current expanding one. The quantum nature of space-time allowing the cosmos to pass through what would otherwise be a singular point. But, like string theory, loop quantum gravity has not yet been confirmed by experiment. The scales at which its effects would become apparent are far too small to probe directly, and the predictions it makes about larger-scale phenomena are subtle and difficult to test. We should also speak of the graviton, the hypothetical particle that would carry the gravitational force in a quantum theory. In quantum field theory, forces are transmitted by particles called gauge bosons. The electromagnetic force is carried by photons, the weak force by W and Z bosons, the strong force by gluons. If gravity is to be brought into this framework, there should be a corresponding particle, the graviton, which would be massless, travel at the speed of light, and have a property called spin equal to 2. Theoretical calculations can describe what properties a graviton should have, and they are consistent with the behavior of gravity as we observe it. But no graviton has ever been detected directly. Gravity is so extraordinarily weak compared to the other forces that the interactions of individual gravitons with matter are vanishingly rare. Building a detector sensitive enough to capture a single graviton is, with current technology, essentially impossible. The graviton remains a theoretical necessity, a particle that should exist if gravity is truly quantum mechanical, but one that has never been seen. And this weakness of gravity brings us to another deep mystery, known as the hierarchy problem. Gravity is, by an almost absurd margin, the weakest of the 4 fundamental forces. The electromagnetic force between 2 electrons is approximately 10 to the 36th power times stronger than the gravitational force between them. That is a 1 followed by 36 zeros. And yet, despite its weakness, gravity is the force that shapes the universe on the largest scales, that holds galaxies together, that causes stars to form and planets to orbit. The reason is that gravity, unlike the other forces, is always attractive, and its effects accumulate without cancellation. Matter attracts matter, and more matter attracts more matter still, and so on the scale of planets and stars and galaxies. Where vast amounts of matter are gathered together, gravity dominates. But why is gravity so weak in the first place? Why is there such an enormous gap between the strength of gravity and the strength of the other forces? This is the hierarchy problem, and despite many clever proposals, no one knows the answer for certain. Some physicists have suggested that gravity may not actually be weak, but may only appear weak because it spreads into extra dimensions that the other forces cannot access. In certain versions of string theory, for instance, the particles that make up ordinary matter are confined to a three-dimensional membrane, a brain, embedded in a higher dimensional space. But gravitons can travel through the full, higher dimensional bulk, diluting their strength. Other proposals involve new symmetries or new particles or modifications to the structure of spacetime itself. But none of these ideas has been confirmed, and the hierarchy problem remains one of the great open questions in fundamental physics. And so we find ourselves here, at the edge of what is known, contemplating a beautiful, unsolved mystery. Gravity, the most familiar of forces, the one that keeps us gently pressed against our beds as we drift toward sleep, is also the most mysterious. It refuses to fit neatly into the quantum framework that describes everything else. It predicts its own failure in the hearts of black holes and at the dawn of time. It is weaker than it has any apparent reason to be. The smallest things, the Planck scale fluctuations that should govern its quantum behavior, remain hidden from us, inaccessible to our instruments and our experiments. String theory and loop quantum gravity and other approaches offer tantalizing glimpses of what a deeper understanding might look like, but the final answer remains elusive, and may remain so for some time yet. There is something rather peaceful in this. If you allow yourself to feel it, the universe still has secrets, deep and fundamental ones, that the finest minds have not yet unraveled. Gravity, which we experience every moment of our lives, which holds us to the earth and the earth to the sun, is at its foundation a mystery. We understand its effects with extraordinary precision. We can calculate the orbits of spacecraft and the bending of light and the ripples of gravitational waves. But we do not yet understand what gravity truly is at the deepest level. And perhaps this is fitting, that the force which cradles us each night, which pulls our eyelids gently downward and draws us into sleep, should also be the one that guards the universe's most profound secrets. Rest now, and let the questions settle softly around you, unanswered and untroubling, like starlight falling through the dark. And so we now move outward, as one does when the hour is late and the mind is ready to drift, and we will consider the very largest things that can be considered at all. The structures so immense that even our own galaxy, with its hundreds of billions of stars, becomes little more than a single mote in an unimaginably vast arrangement. And in doing so, we will discover something rather soothing, which is that everything, needs, at every scale, is falling towards everything else, always, and has been doing so since the beginning of time itself. You will recall, perhaps, that we have spoken of how you are falling toward the Earth, and the Earth is falling toward you, and how the moon falls toward us as we fall toward it, and how our planet falls endlessly around the sun, while the sun itself drifts through the galaxy. And now we must acknowledge that even our galaxy, the Milky Way, this great spiral of stars and gas and dust that stretches 100,000 light-years from edge to edge, is itself falling, has always been falling, and will continue to fall for billions of years to come, drawn by the patient and invisible hand of gravity towards something so massive, so distant, and so mysterious that astronomers have given it a name that suits its nature rather well. And that name is the Great Attractor. The Great Attractor lies approximately 250 million light-years away from us. in the general direction of the constellation Centaurus, which you might find in the southern sky if you were standing in a quiet field somewhere below the equator on a clear night. Though, of course, you would not be able to see the great attractor itself. Not because it is too far away, though it certainly is very far away indeed, but because something closer to home obscures our view, and that something is our own galaxy, which is to say, the Milky Way itself, whose dense band of stars and dust and gas runs across our sky and blocks our telescopes from seeing what lies beyond in certain directions. And astronomers have a rather lovely term for this obscured region. They call it the zone of avoidance, because for a long time that is precisely what they did. They avoided it, as one might avoid a doorway that leads only to a darkened room in which nothing can be discerned. But gravity, as we have discussed in earlier passages, does not require us to see what is pulling us. Gravity reaches through the dark, through the dust, through hundreds of millions of light years of empty space. And so, even though the great attractor remains hidden from our optical telescopes, we know it is there because we can feel its pull. Or rather, we can measure the motion that its pull creates, and that motion is considerable for our entire local group of galaxies, which includes not only the Milky Way, but also the Andromeda Galaxy and dozens of smaller companions, is moving toward the great attractor at a speed of approximately 600 kilometers per second, which sounds extraordinarily fast because it is extraordinarily fast. And yet, at such distances, this motion will take an almost incomprehensible span of time to carry us appreciably closer. And so, there is no cause for concern, only for a gentle sort of wonder at the scale of things. The story of how astronomers came to understand the great attractor is one of patient observation and careful measurement, and it involves a group of 7 researchers who worked together in the 1980s and who came to be known, with a certain affectionate informality, as the 7 Samurai, a reference to the famous film by Akira Kurosawa. And among these 7 were Alan Dressler and Sandra Faber, both of whom made significant contributions to our understanding of how galaxies move and why they move in the directions they do. In 1988, this group published their findings, which showed that the motions of many galaxies in our region of space could not be explained by the gravitational pull of visible matter alone. That there must be something out there, something with tremendous mass, something hidden behind the zone of avoidance, pulling us all toward it. And they named this something the great attractor, and the name has remained with us ever since. A quiet acknowledgement of the force that guides our motion through the cosmos. Now, when we speak of falling toward the great attractor, we must be careful not to imagine this as a simple matter of one destination, one final point towards which everything converges, for the universe is not so neatly organized. And the great attractor itself is part of a larger structure, a much larger structure, one that was only fully mapped and named in the year 2014 by an astronomer named Brent Tully, who works at the University of Hawaii, and who gave this structure a name from the Hawaiian language, Laniakea, which translates to something like immense heaven. And that is a fitting name indeed. For Laniakea is the supercluster to which we belong, our cosmic address, if you will, a vast region of space containing approximately 100,000 galaxies, all of which are bound together by gravity, all of which are falling toward one another in the slow and patient dance that gravity choreographs across the ages. To understand Laniakea, it helps to imagine that you are looking down upon a great basin, a depression in the landscape of space, and at the bottom of this basin, or near the bottom, lies the great attractor. And all the galaxies within this basin are rolling slowly downhill toward that lowest point, drawn by gravity, just as water is drawn toward the drain of a bathtub. Though of course the analogy is imperfect, as all analogies must be. For in truth, the galaxies are not moving through a landscape, but rather through space itself. And the basin is not a physical depression, but rather a region where the density of matter creates a stronger gravitational pull. And yet, the image of rolling downhill is not entirely wrong either. For in a very real sense, that is exactly what is happening. Everything is falling towards everything else, and the great attractor is simply the direction in which much of our local universe is falling at the moment. If one can use the word moment to describe a process that unfolds over billions of years. And there is more. For beyond the great attractor, further out into the depths of space, lies another concentration of matter, even more massive, a structure known as the Shapley supercluster, which was first catalogued by the astronomer Harlow Shapley in the 1930s, and which we now know contains thousands of galaxies packed into a relatively small region of the cosmos. And it is towards this supercluster, in part, that the great attractor, and all of us along with it, may ultimately be falling, though the details of these motions are still being worked out by astronomers who spend their lives measuring the red shifts and blue shifts of distant galaxies and calculating the invisible forces that guide their paths. If you were to zoom out still further, to a scale at which even superclusters become small, you would begin to see the largest structures in the observable universe, the great filaments and walls and voids that together make up what astronomers call the cosmic web. And this web is not something that was designed or planned. It is simply what happens when you let gravity work upon matter for 13.8 billion years, which is the current age of the universe, give or take a few million years. And over that time, gravity has pulled matter together into denser and denser regions, leaving vast empty spaces between them. And the result is this web-like pattern, with long filaments of galaxies stretching across millions of light years, and great voids where almost nothing exists at all. And at the intersections of these filaments lie the densest concentrations of galaxies, the superclusters and clusters that contain most of the light and most of the mass in the cosmos. This cosmic web is, in a sense, a sculpture made by gravity, a work of art 13.8 billion years in the making, and it is still being made, still taking shape, as galaxies continue to fall toward one another and clusters continue to grow and filaments continue to draw matter out of the voids. And all of this happens so slowly that no human lifetime could ever perceive the change. But the change is real nonetheless, and we are part of it, falling along with everything else toward destinations we cannot see and may never reach. And yet, there is a mystery here, a puzzle that has occupied astronomers for decades and that remains unsolved to this day. And it concerns the question of how much matter the universe actually contains, and where that matter might be hidden. For when astronomers measure the motions of galaxies, when they calculate how fast galaxies rotate and how strongly they pull on one another, they find that the numbers do not add up, that the visible matter, The stars and gas and dust that we can see with our telescopes is not nearly enough to account for the gravitational forces that are required to hold galaxies together and to pull them toward one another in the patterns we observe. This discrepancy was first measured carefully by an astronomer named Vera Rubin, who in the 1970s turned her telescope toward the Andromeda Galaxy, our nearest large neighbor in space, and measured the speeds at which stars in that galaxy were orbiting around its center. And what she found was remarkable and troubling, for the stars at the outer edges of Andromeda were moving far too fast. Fast enough that they should have been flung out into intergalactic space by centrifugal force. And yet they remained in their orbits, held in place by gravity, which meant that must be far more mass in Andromeda than the visible stars alone could provide. And this extra mass, whatever it might be, came to be known as dark matter, a name that captures both its invisibility and our ignorance about its true nature. We now believe, based on many observations and calculations, that approximately 85% of all the gravitational mass in the universe is made of this dark matter, this invisible substance that we cannot see with any telescope, that does not emit light or absorb light or scatter light in any way that we can detect. And yet it pulls on ordinary matter with its gravity, shaping the rotation of galaxies and the motions of galaxy clusters and the very structure of the cosmic web itself. And we are surrounded by it, embedded in it, falling through it and toward it at every moment of our lives, though we cannot see it and do not yet know what it is made of. So when we say that you are falling, we must acknowledge that you are falling toward many things you cannot see, toward dark matter that surrounds our galaxy like an invisible halo, toward the great attractor hidden behind the zone of avoidance, toward structures and masses that lie beyond the reach of any telescope we have yet built. And there is something strangely comforting in this, in the idea that gravity connects us to the invisible as well as the visible, that we are part of a cosmos far larger and stranger than what our eyes alone can perceive, and that we are held, always, by forces we cannot see, falling gently through a universe that is itself held together by the invisible. And with this thought, we might let our minds settle into the darkness, into the soft and patient falling that carries us all, every star and every galaxy and every mote of dust, toward destinations we will never see, moving always at 600 kilometers per second and yet feeling nothing at all. For that is the nature of falling in space. It is silent, and it is gentle, and it never ends. And so we return now to you, lying quietly wherever you happen to be, your breath moving in and out in that ancient rhythm that requires no thought at all, your body settled against whatever surface holds you, your eyes perhaps closed or perhaps growing heavy, and all the while, without any effort or intention on your part, you are falling. You have been falling this entire time. You will continue to fall long after these words have faded into the soft edges of sleep. Because falling is not something that happens to you occasionally, not something that interrupts the stillness of your life, but rather the very medium through which your existence unfolds. The constant and unwavering truth of what it means to be a physical thing in this particular universe, at this particular moment, in this particular arrangement of matter and energy and curved space-time that we call home. You are falling right now at approximately 107,000 kilometers per hour as the Earth carries you around the Sun. And the Sun itself is falling through the Milky Way at about 828,000 kilometers per hour, dragging the Earth and all its passengers along in that great spiral journey through the galactic disk. And the Milky Way is falling towards the Andromeda Galaxy, and both of them are falling together toward the Great Attractor, that mysterious gravitational anomaly hidden behind the dust of our own galaxy, pulling hundreds of thousands of galaxies in a silent procession across the void. And all of this falling happens without the slightest sensation of motion, without any rushing wind or lurching stomach. Because in the language of curved space-time, falling is not motion at all, but simply existence, simply the natural progression of a body through the geometry of the universe, following the gentle contours that mass has pressed into the fabric of space and time. To fall, then, is not to fail, not to lose control, not to plummet toward some catastrophic end, but rather to participate, to take your place among all the other falling things, to join the endless company of matter that has been falling since the very first moments after the universe began its vast expansion, when gravity first began to gather the scattered hydrogen into the clouds that would become the first stars, when falling became the mechanism by which complexity could emerge from simplicity, by which the uniform became the structured, by which the possibility of planets and oceans and breathing creatures could slowly, patiently, inevitably unfold across billions of years of cosmic time. There is an image that may be worth holding gently in your mind as you settle deeper into stillness. An image captured on the 14th of February in 1990. When the Voyager 1 spacecraft, having completed its primary mission of photographing the outer planets, turned its camera back toward the inner solar system from a distance of approximately 6 billion kilometers, and took a series of photographs that included one showing Earth as a tiny point of light, a pale blue dot suspended in a beam of scattered sunlight, barely distinguishable from the noise in the image, a fraction of a pixel in the vast darkness of space. The astronomer Carl Sagan, who had requested that photograph be taken, later reflected on what that image revealed about our place in the cosmos, noting that on that tiny speck, everyone you have ever heard of, every human being who ever lived out their lives, that all our triumphs and tragedies, all our wars and religions, all our hunters and foragers and kings and peasants and young couples in love, existed on that mote of dust suspended in a sunbeam. And that pale blue dot, that fragile point of light in the immense darkness, is falling, has always been falling, will continue to fall for billions of years to come. And everyone who has ever stood upon its surface was falling too. And everyone who will ever stand upon it will fall alongside it. And the falling is not a predicament to be escaped or a problem to be solved, but simply the way things are, the quiet truth at the heart of existence, as ordinary and as extraordinary as breathing, as sleeping, as being the atoms that compose your body, the calcium in your bones, and the iron in your blood, and the carbon that forms the scaffolding of every organic molecule within you. These atoms were not always part of you, were not always part of the Earth, were not always part of this solar system at all, but were forged in the hearts of stars that lived and died long before our sun was born. Stars that burned through their nuclear fuel over millions of years and then collapsed under the weight of their own gravity, falling inward upon themselves with such tremendous force that they exploded outward in supernovae, scattering their newly minted heavy elements across the interstellar medium, seeding the clouds of gas and dust that would eventually collapse under gravity once more to form new stars, new planets, new possibilities for complexity and life. You are, in a very real and non-metaphorical sense, the child of gravity, assembled from the debris of gravitational collapse, given form by the same force that shapes galaxies and guides the orbits of moons, participating in a story that has been unfolding for nearly 14 billion years and shows no sign of ending anytime soon. This is not to say that the story will unfold forever, of course, for the universe appears to have a trajectory, a direction in which time and entropy carry all things, and the most widely accepted models of cosmology suggest that our universe will eventually reach a state of maximum entropy, a condition sometimes called heat death, in which all the stars have burned out and all the black holes have evaporated through Hawking radiation, and all the matter has decayed into a thin, cold, uniform mist of particles drifting through an ever-expanding darkness, with no gradients of energy left to drive any processes, no complexity remaining to observe or be observed. Just a vast, silent, eternal equilibrium stretching on forever. Some models suggest an alternative fate called the Big Rip, in which the accelerating expansion of space eventually tears apart galaxies, then solar systems, then planets, then molecules, then atoms themselves, until nothing remains but a foam of disconnected particles racing away from each other faster than light. These endings lie unimaginably far in the future, trillions upon trillions of years from now, so distant that the current age of the universe would seem like a brief flash at the beginning of an almost infinitely long story. And for now, for this brief cosmic moment in which stars still shine and planets still orbit and living things still breathe and think and dream, gravity continues to gather matter into warmth and form and continues to hold you gently against the surface of the earth, continues to provide the structure within which all the things you love can exist. In the town of Princeton, New Jersey, in the years following the Second World War, there was an elderly man who could often be seen walking along Mercer Street in the early morning, making his way from his modest home to the Institute for Advanced Study, where he held a position that made no demands upon him other than to think about whatever he wished to think about. This was Albert Einstein, whose work on general relativity had transformed our understanding of gravity from a force acting at a distance to a curvature in the fabric of space-time, who had shown that falling bodies are not being pulled downward but are simply following the straightest possible paths through curved space, who had revealed that what we experience as gravity is really the shape of the universe itself. In those later years, Einstein walked slowly, often lost in thought, still puzzling over questions that had occupied him for decades, still trying to reconcile his theory of gravity with the strange new physics of the quantum world, still wondering whether the universe might be described by some deeper, simpler principle that he had not yet glimpsed. He never found that unified theory he was looking for, never managed to combine gravity with the other forces of nature, and to this day, nearly 70 years after his death, no one else has found it either. Though many continue to search, the nature of gravity remains, in some fundamental sense, a mystery, something we can describe with extraordinary precision, but cannot fully explain, something that continues to reveal new puzzles the more carefully we examine it. And perhaps there is something appropriate about that, something fitting about the idea that the force which holds you to the Earth and guides the motions of galaxies should retain some element of the unknown, some depth that resists our complete understanding, not because the universe wishes to hide itself from us, but simply because understanding takes time. And we have not had very much time yet, not on the cosmic scale of things. And there is still so much to learn, so many questions to ask, so many patient measurements to make and careful thoughts to think. And none of that needs to happen tonight. None of that requires your attention now, as you lie quietly in your own small corner of the falling universe, as your breath continues its slow rhythm, as your thoughts begin to soften and blur at the edges, lying still. You may feel as though nothing is happening, as though you have come to rest, as though motion has ceased and stability has been achieved. But this is an illusion, a gentle and forgivable illusion created by the remarkable synchrony of your falling with everything around you. The way you and the bed and the building and the earth all fall together through space-time, following parallel paths that never diverge, maintaining their relationships to one another even as they trace their endless curves through the geometry of the cosmos. You have never been still, not for a single moment of your existence, not when you were an infant sleeping in a crib, not when you sat quietly in a classroom, not when you lay awake in the darkness wondering about the future. Because stillness in the absolute sense does not exist in this universe. Only relative stillness, only the appearance of rest that comes from falling alongside everything else, from participating in the same great motion that carries all things forward through time and space. And this falling, this constant participation in the motion of the universe, is not something that requires your effort or your attention or your understanding, is not something you need to manage or control or even think about, but simply happens, has always happened, will continue to happen whether you are awake or asleep, whether you are young or old, whether you remember these words or forget them entirely, because falling is what matter does. Falling is how existence expresses itself in a universe shaped by gravity. Falling is the medium through which you have lived every moment of your life and will live every moment still to come. So let yourself fall now. Let yourself continue the falling that has never paused. Let your thoughts fall gently towards sleep. Let your awareness fall softly into that quiet darkness where dreams may or may not await, knowing that you are held not by any surface or any force in the ordinary sense, but by the very shape of space-time itself, cradled in the curves that mass has pressed into the fabric of reality, supported by the geometry of the universe in an embrace that has no edges, no gaps, no possibility of failure. You cannot fall out of this falling, cannot escape it, cannot be abandoned by it, because it is not something that happens to you, but something that you are, something that everything is. The most fundamental truth of existence in a cosmos where gravity is not a force pulling you down, but a shape holding you in. The darkness between the stars is vast, and the silence of space is absolute, and the distances that separate the galaxies grow larger with each passing moment as the universe continues its ancient expansion. And yet, Here, on this small planet, in this brief window of cosmic time, gravity has gathered matter into the warmth of stars and the solidity of rock and the intricate complexity of living things, has made possible the existence of creatures who can lie quietly in the dark and wonder about the nature of reality, who can feel their breath moving in and out and know that they are part of something far larger than themselves, who can let sleep arrive like gravity itself, soft and inevitable and everywhere, requiring nothing, asking nothing, simply being what it is and doing what it does, as it has always done, as it will always do. In this falling universe, where to exist is to fall, where to fall is to be held, where to be held is to rest at last in the arms of everything that is.